Let's turn our attention now to brushless DC motors. And you'll see that the topology is actually quite different from a brushed DC motor in the sense that the coils are now actually on the stator and the permanent magnet is on the rotor. So it's like we took our brushed DC motor and flipped it inside out to create this topology. And what I'm going to do is I'm going to pass some current through this coil in such a way that it creates a north pole in the air gap on the top stator piece, and it'll create a south pole in the air gap on the bottom stator piece. Now I'm going to put a hand crank on this motor, and I'm going to essentially rotate it through 360 degrees, as you can see here. And what I'm doing is I'm plotting the torque that the motor is generating as it's rotating. Now I will tell you that I've never seen a motor that had this beautiful of a torque waveform, and it's almost impossible to achieve because you would have to have uniform flux density in the air gap in order to get that kind of performance, and no motor can achieve that. But for the moment, let's just assume that that's what I've got and that that's what the waveform looks like. So right there at angle equals 0, we see that that's not a point that the motor wants to be in because I've got a north pole fighting against a north pole and a south pole fighting against the south pole. But nonetheless, all the force that's being produced on that rotor is right through the center of it, so therefore the net torque is 0. And if I knock it off of that center position by just a little bit, it's going to swing around to this position right here, and that's where the motor actually wants to be, where I have attraction between the rotor and stator magnets. And if I try to offset that rotor from that position, either from a clockwise point of view or a counterclockwise point of view, notice the torque that the motor produces. It actually fights me to get back to that state where it wants to be at, which is, sometimes I refer to that as the happy state of the motor. So the motor's just sitting there, it's all happy and everything, but it's not producing any torque for me. How do I get the motor to actually rotate another 180 degrees? Well, the answer is I need to change the polarity of the currents in my stator coils. So if I do that, what that essentially does is that will now invert the torque curve from its original position. But the problem is, in order to get back to that other angle, 0 degrees, I don't know whether it's going to go in a clockwise direction or a counterclockwise direction. It's actually undefined. A perturbation in either direction could send the motor flying off in that particular direction. So this non-deterministic performance of this single-phase brushless DC motor is not acceptable, and we need to find a way to get around that, and that's done in the next slide. So to get around this undeterministic nature in terms of which direction the motor will want to spin, the solution is we add more phases to the stator. So in this case right here, I'm going to turn on some current to phase A. And when I put a rotor inside that stator structure, it's going to line up in the direction as shown here. Now what do you suppose I would have to do in order to get the motor to spin in a clockwise direction? Well, the answer is I would want to take the current out of phase A and put it into phase C. In particular, in this case, it would be negative current into phase C, and that will cause the rotor to now try to line up with the phase C stator poles. Now this process of taking the current out of one coil and putting it in another coil, it has a specific name in motor control. It's called commutation. And basically, commutation means taking the current out of one circuit and putting it into another circuit. So in this case, I've taken the current out of coil A, I've put it in coil C, and the rotor now wants to align with the stator poles of coil C. And I can continue this commutation process and make the motor continue to spin around following the rotating magnetic field of the stator as shown in this diagram. However, this is not a very efficient way to control a brushless DC motor. In fact, if you look, I'm only controlling one stator phase at any given time, and that means that 2 out of the 3 coils are not being used for anything. There's actually a better way to do it, and let's take a look at that in the next slide. So here I have my 3-phase stator arrangement with the rotor inside of it. And what I'd like to do is to come up with a procedure by which I can drive multiple coils to generate positive or negative torque. So the way I'm going to do this is I'm going to put positive current into all 3 phases of the motor at the same time. And then once again I'm going to put like a hand crank on the motor, and I'm going to spin it, I'm going to rotate it very gently through 360 degrees. Now the torque waveform that you see for phase A, that's the same one that we saw in the first slide when we talked about brushless DC motors. But what you'll notice is that the torque waveforms for phase B and phase C are identical to this. The only difference is they're separated in phase by 120 degrees, and that's because the B and C coils are separated from phase A spatially by 120 degrees. So we end up with torque waveforms that look like this. Now, by looking at each one of those commutation intervals, here's the rule that I'm going to apply. If positive current